Welcome, everyone. Thank you for all for being here. And if you have later on, as I ask questions of everyone, if you're uncomfortable answering questions, this isn't supposed to be stressful, just say pass. I don't want to make anyone unhappy. And I know when I was taking this class, I was always happy if I thought I had the right answer. And so back when Ralph, I'm trying to think of what Ralph's last name is over there in Iowa, had this class online. But if you do have a question, I'm going to be monitoring the chat tonight. Are you with us, Samantha? Let me see if Samantha's in here. She might be getting here a little later. She might have a flotilla meeting or something like that. I'll be monitoring the chat. Our next presenter served as the district staff officer for member training for my district, 9th Western. And he's been teaching public education classes like nobody's business in downtown Chicago. So we're very proud of him out here at 9th Western. And anything else? And with that, I'm going to give it to you, Dan. Anything else you want to share about yourself?
No, the only thing, well, I want, first of all, welcome everybody. Those of you who are comfortable doing it, either because you know how and want to, or if you don't know how or don't want to, don't worry about it. But I know we're from like everywhere, and as I glance, it might be interesting for me to see some names I recognize. I know who you are. Hello. Others I haven't a clue. So I'd like to kind of have a sense of, am I talking to Europe? Am I talking to Michigan or Kentucky or wherever? I think that, so if you can change or rename yourself just to add your city, that'd be great. Jock, you raised your hand. You have a question already.
I thought that's where you were going. Jock Whittlesey and Monique Wong from Jupiter, Florida.
Okay. Well, welcome. I think your weather down there is probably a whole lot different and better than ours. We have stratocumulus outside tonight, which will, by the time we're done with tonight's conversation, you all will know what that looks like. But we're going to talk about clouds. There's going to be a lot of pictures used in this. And just by way of background, and thank you, Bob, for the introduction. I've been in the auxiliary for coming up on 9 years now. I've been the public education officer in our flotilla for, I think, 6 of those 9 or something like that, maybe more. I used to be, among other things in my previous life, an educator teaching at the university level. And so I had 2 rules in my classes, only one of which is going to apply tonight. The first rule was if your cell phone rings, I would answer it. That's the one that's not going to apply tonight. The other one was that there were no rules. So if you've got questions, if I start to go off on a tangent or I start to be confusing and not helpful, you know, please raise your hand, put a question in the chat room or in some other way, make sure that I know that you've got a question or an issue and we can address it on a timely basis. So I'm going to share my screen if we're ready for that, Bob.
Fire away. And we'll go with our previous effort, which is put it in the chat first. And if I don't have a good answer for you, I'll interrupt the class.
Okay, can everybody see the screen that says aux weather and clouds and all that other stuff?
Looking good.
Okay, I'm looking for my little advancing device here. When I teach, I don't like to spend a lot of time on sections and introductions. I know the format when you're teaching, especially in the service or the government, is tell them what you're going to teach it, and then remind them what you just taught them. I don't want to spend a whole lot of time being duplicative to what we're going to talk about when we get into the body of the conversation tonight. You know, so this is a whole bunch of overviews. You will see all those topics covered in the next handful of slides. So, yeah, when I was reading this, I was trying to figure out, well, what are clouds and what's the easiest way for people to think about it? And the example that came to mind was what happens when relative humidity is 100%, or another way, when the dew point and the air temperature are equal, what happens down here at the surface. Anybody want to tell me? What do you get when you're at 100% humidity, when the temperature falls down to the dew point overnight? What do you wake up to in the morning?
Condensation.
Rain.
Well, maybe rain, but certainly
Sticky
fog.
and sweaty.
Yeah, you
Fog.
get, and all a cloud is fog, not at the surface. Yeah, so it's a collection of, depending on the altitude and the temperature where it forms, it's either a bunch of water, very small water droplets, or small ice crystals. And it's, as the slide suggests, it forms when the dew point and the air temperature are equal. And as you've heard earlier in the class, you can get to that point one of two ways, either lower the temperature or raise the humidity. Clouds are classified a couple of different ways, and there'll be a slide coming up that sort of is a chart that puts these two together. You know, the first way that clouds are classified is by height. You know, so there are low clouds, there are middle clouds, and there are high clouds. And low clouds are anything less than 2,000 meters, or about 6,500 feet in altitude to their base. High clouds are anything where the base starts at 20,000 feet and goes up. So if you remember, low is 2,000 meters and below, and high is 6,000 meters and above, you know, then the stuff in between is called the middle. Clouds are also classified by their appearance, where, you know, they can either be lumpy. When I think of cumuliform, I think of like cauliflower. And a lot of this stuff comes from Latin words. So cumuliform, it comes from cumulus, which in Latin says, you know, to make a pile or to heap on. Stratiform comes from, actually it's derived from a verb we don't need to get into, but essentially it means to cover something or to make a layer. And then cirriform comes from the Latin word cirro, which is Latin for a curl of hair, which I found that out preparing for this class. So it's and if you think about it, when we look at the pictures of the cirrus clouds that come up later in tonight's conversation, you can see why they would have thought that comes like a curl of hair. So low clouds typically are created by water droplets, just because the air temperature is not, other than here in this latitude, 90% of the time, it seems like, it's formed by water droplets that coalesce into or form into a water droplet formed cloud. So you've got low clouds that are cumulus, which again, we'll see pictures of all this stuff in a minute. But those are the small kind of puffy clouds that you see in the sky. And stratus clouds are the ones that sort of have been what we've had in Chicago for about 4 months, which are kind of low, gray, ugly. It looks like it's going to rain, but it never does. You know, those are stratus clouds. Stratocumulus are kind of sort of a hybrid in the sense that they're not as plain as stratus clouds would be. They're not as neat because they've got a little bit of puffiness or fuzzy edge to them. Again, we'll look at these things in a minute and see pictures. Nimbostratus, a couple of things in terms of prefixes or suffixes you're going to want to remember. If you see nimbo or nimbus, that means that that particular cloud is producing precipitation. So if it starts with a nimbo or ends with a nimbus, that means it's starting, it has precipitation in it. Alto, and I was trying to figure out, well, what's a good way to sort of get you to think about this? If you think about a choir, those of you who sing or go to church and hear people singing, you have bass, which are the lower voices. And in this case, bass with an E is the low clouds that we talk about. You have altos, which are the middle voices in a choir. And then you have sopranos. Well, we don't exactly have a soprano. We do have a cirro, C-I-R-R-O, or cirrus, if it's the cloud specifically cirrus. You know, so think about altos are middle, bass is low, and sopranos or cirros are the high clouds. And then there's different kinds of each of them. And then there's a fourth type of cloud, which isn't really a type, but it's just sort of a, hey, we throw everything else together because they come about by vertical development. We'll talk a little bit more about that in a little while. I said that there was a chart, and this is the chart that kind of throws those two measurements. So over on the left side, you've got the type. So you've got the cumuliform, the stratiform, and the cirriform. So cumuliform is low, stratiform is middle. Excuse me, stratiform is that flat kind of layer, and then cirriform is the curly hair. And then across the chart, you've got the altitudes at which those clouds typically form. You know, so you can have cumulus clouds at any of the three altitudes, either low, middle, or high. You could have stratus clouds, stratiform clouds at any of the three altitudes where clouds are forming. But only cirrus clouds will form at the high altitude. Everybody got that? Any questions? Because this is a good summary of how clouds are characterized and described and where they all fit in the various layers of the atmosphere that we're looking at. And it's important to remember that low clouds have a base, or your base clouds, no higher than 6,500 feet. So the base is going to be something less than 6,500, roughly 2,000 meters. And the high clouds start at 20,000 feet, which is roughly 6,500 meters. Okay, any questions so far? Cumulus clouds. I mean, these are small, puffy. I mean, we see them during the summer all the time. I know the book talks about, they say they very rarely produce precipitation, but I put an asterisk after that, because if in fact they break through the stabilizing cap that's over the layer in which they form, you know, they're formed by the heat of the day causing air to rise, and then if they come out, and then they're normally capped. But if they break through that cap and get into unstable air, they become not so nice. You know, we usually like to see these when we're out on patrol, unless it's a hot summer day and there's the potential for them to pop up into a thunderstorm, which is what happens when they break through the stabilizing cap. Stratus clouds, remember, these are the flat, uniform, think of layers of cake kind of thing. When you're down below them, they're kind of gray and ugly, and the darker the cloud, the thicker they are, more layers, maybe a little bit more higher number of water droplets in them. They're not raining because there's not a nimbo or a nimbus associated with these specific clouds. You know, but if you're above them, and this picture is obviously taken from a mountaintop looking down into a valley, they look white because the sun's shining on them. When you're below them, they look dark because the sun can't get through them. Stratocumulus clouds, this is the ones that are kind of a combination of the two, where if you take a lot of cumulus clouds and you smush them together so that you're starting to get a layer or a cover or a blanket of clouds, they kind of remind you of stratus clouds, but they have a cumulus feature in that you can see rough edges and puffiness, and they're fuzzy, like this slide says. Nimbostratus, I've circled the rain shafts coming out of these two pictures, out of the clouds in these two pictures. The fact that you have nimbo in them as a prefix says that they are forming some kind of precipitation that is coming out of the clouds. Doesn't always or necessarily make it to the ground, but it at least is sufficiently, the droplets are sufficiently heavy that they're falling from the clouds and you can see them. Altocumulus, again, cumulus clouds can be formed in any of the three levels that we're talking about. So alto is, where is that in our choir? Anybody?
Middle.
Middle. So alto's in our middle layer. So they're cumulus clouds that have formed somewhere between 6,500 and 20,000 feet. They can be random, or they could be like this picture, which shows streets. And, you know, when I see this, I always think about a beach, where if you look down into the water, where the sand is, you can see where the waves have created ripples in the sand. That's essentially what's happening here, where the river of air, the jet stream or whatever is moving, is creating waves where clouds are being formed in those waves, and that's what you see. The streets show the direction of the upper winds, but you have to remember that just like a wave creates a ridge or a ripple in the beach, in this case, the waves that create these clouds are moving perpendicular to the streets. So if you want to know, well, where's the wind coming from? In this case, it's coming from right to left, probably, or left to right. But in any case, it's in either case, it is perpendicular. The wind direction is perpendicular to the streets that you see in the clouds. Alto stratus. Alto, again, is mid-level. And stratus clouds, we typically think of them as being kind of that ugly sort of low-hanging, dreary clouds that are out there. And that's true when they're formed, you know, in the low level, below 6,500 feet. But when they're in the middle level, they kind of look like stratus clouds. They're not as dreary. They're still overcast. And they just look higher in the sky. I'm not sure. That's kind of a scientific term, probably not terribly precise. When the clouds are thin enough, if the clouds are so thick that the sun can't shine through, then you don't see anything. But if the clouds are thin enough, you see a corona. And we're going to talk about coronas, and we're going to talk about halos and rainbows later, you know, but essentially, you'll see a corona, which, you know, in this picture is the Eiffel Tower with a bright spot behind it. And that bright spot is, in fact, the sun, obviously enhanced by the corona effect that is going on there. Cirrus clouds are only formed at the high level, and they're all ice clouds. You know, the other ones might be water droplets or a combination of water droplets and ice crystals. Cirrus clouds are all ice particles. And we're going to talk about, you know, what does that mean when we get into, well, gee, what's the difference between water and ice when it comes to light, and what sort of effects does that create for us? But I hope you can all see how cirro, the hair, curly hair thing comes out of here, because it's fine filaments. In fact, and not all cirrus clouds have a tail, a mare's tail, kind of looks like a horse's tail. But when they do have clouds or a portion of the cloud that curves upward and forms kind of an arrow, you know, the wives' tail, if you will, is that mare's tails tend to point in the direction that a storm is approaching from. And that can be true. You know, it depends a little bit, because oftentimes cirrus are the ice particles blown off the top of thunderstorms or storm clouds further upstream in the jet stream. You know, so they can be a harbinger of what's coming. How quickly it comes, it kind of depends on whether it's a warm front or a cold front. Because if it's a warm front, then it'll probably be in the next 24 hours or so. If it's a cold front, it might be longer, it might be shorter. It really depends on how fast the cold front is advancing. And so, but it does give you a sense that precipitation is upstream, and if it holds together, it's going to be in your area sometime in the next day, more or less.
And Dan, we had a question from Mark Bagley.
Yes.
Those cirrocumulus clouds on the bottom right of that image?
Yes, you can in fact have they oftentimes come together because at that altitude, you get a mixture of things in there. So yeah, you can have cirrocumulus clouds, nice call, or you can have just cirrus clouds. So the two usually show up together, as a matter of fact. Cirrus stratus clouds, these again, stratus clouds can be formed at any of the three levels, and these are the high altitude stratus. So you've got a really thin blanket, if you will, at that altitude, but that is covering the sky. And they are ice clouds, and ice clouds form halos. So if you see a halo around the sun, you are seeing cirrostratus. If you're seeing a corona, or like the sun looks bigger than it would if you were just looking appropriately at it, then that's an altostratus cloud. So this obviously is a halo around the sun, and that means the sun is shining through the cirrostratus clouds. Cirrocumulus, we good catch before, but these are similar to altocumulus, but again, because they start with the cirro prefix as opposed to the alto prefix, it means they are cumulus clouds above 20,000 feet. They are still those puffy kinds of cumulus clouds that we knew and saw as fair weather clouds on a summer day. They look like they're smaller, but that's because they're like 3-4 times the distance away from our eye. But those are in fact those same kind of fair weather puffy clouds that you would see. If the whole sky is filled with them, that's called mackerel skies. And as the book suggested, on a winter day, a mackerel sky is oftentimes a good thing because it suggests, that fair weather is coming. In the winter, it's not necessarily so, because anytime clouds form at 20,000 feet or higher, it's an indication that there might be something downstream, or excuse me, upstream from us headed our way downstream. So it can be an indication in the summer of something, again, approaching. Vertical development clouds, we talked about the cumulus clouds punching through a cap and forming a thunderstorm. Those are vertically developed clouds, and they're typically clouds that are higher than they are wide. They're oftentimes can be unique. The pop-up thunderstorm that we see around here in Chicago, when they're not necessarily in the sense that we're talking here related to a front that's moving through, because they're not contiguous along a front. But the main difference between a cumulus cloud that has gone vertical and a cumulonimbus is that nimbus or nimbo means precipitation. So you have a cumulonimbus cloud that says, hey, rain's coming out of it, or some kind of precipitation, usually rain. And because remember, nimbo or nimbus, nimbo as a prefix or nimbus as a suffix means that the cloud is producing precipitation. And you guys are going to get into a lot of severe weather and more of this stuff in the next chapter. So that's your homegrown pop-up thunderstorm that kind of makes life miserable when you're under one. They can have rounded tops or flat anvil shaped. And again, you'll learn more about this in chapter 6 in a whole lot more detail. Lenticular clouds, I can't pronounce lenticularis very well, so we'll just call it lenticular, are an interesting kind of altostratus cloud. So it's a mid-level stratus cloud, but they're formed when the wind blows over a mountaintop, and then a cloud forms, and it forms in this shape. So it looks like a lens. And if you've ever seen one, it's the kind of thing that people call in and report UFOs and that sort of stuff. They're really very, my son lives in Colorado, so I get out there frequently. I think I've seen this once, but I'm told if you live there, you see it more often. Because again, it requires the winds to be coming up over the mountains and then forming the clouds as they come back over the peak and down the slope. That's when they're creating in that sort of area above the wind coming down the mountain faces where these clouds form and over the top of the mountain. Very pretty. This usually, when I grew up, I was one of those people that was told that Mamata's clouds, or cumulonimbus mammatus clouds, are in fact a sign of huge turbulence and a predictor of tornadoes. I think they've come to appreciate that that sentence is half right. They are a sign of huge turbulence in the clouds. I don't think Bob and other pilots would want to fly into that particular cloud. But it's an indication that in fact, the thunderhead above it is either raining itself out or collapsing under the precipitation, so that the likelihood of a tornado forming is not there. That doesn't mean the severe weather isn't still coming, and that isn't going to be a rough time. But it does mean that for this particular cloud, this particular storm is probably mature and going to be raining itself out sometime in the not so distant future. This is what you see before a tornado is formed. It's a base cloud, a wall cloud at the base of a supercell. And any of you, if you've watched like storm chasers, what have you, they love to find these things because it's out of that you see rotation and tornadoes form. Again, we're going to talk, you're going to talk a little bit about that in the next chapter. There's a different thing that the book referred to called the shelf cloud, which is essentially formed on a gust front, where the downdraft that is pushing out ahead of a thunderstorm as all the precipitation is, I mean, you're literally flushing the water out of a cloud, if you will. When it hits the ground, it creates a gust front, and at the front of that gust front, you can have a wall cloud form. Base wall clouds, excuse me, shelf clouds. Wall clouds are typically at the back of a thunderstorm or towards the back of a thunderstorm as opposed to near the front. And it's where tornadoes most often appear if you're going to have a tornado. Okay, section 1. Any questions on that before we get into section 2? Okay. So we're going to talk a little bit about how's it formed, basic types, and how it works. This I thought was interesting, that a water droplet in a cloud is so much smaller than a raindrop, and that by itself, it doesn't have neither the ice particles or the water droplets that form a cloud have sufficient mass to overcome. They have essentially a terminal velocity of whatever it is, wherever they are. They're not heavy enough to overcome the friction in the air and fall. So, but when they aggregate to a size that has the weight to fall, they can come down in a whole bunch of different, ultimately at the surface in a whole bunch of different ways. We're going to talk about how they start and how they end up as what we see out the window when we're having a day where we're getting precipitation. So there's a couple of different theories about how cloud particles aggregate and ultimately become precipitation. I'm not going to spend a whole lot of time going into them, but the way I see this is there's basically, the collision coalescence process talks about water droplets that kind of crash into each other and stick together and eventually get to be of a sufficient size that they have the weight to fall, where the Bergeron process is kind of, you're accumulating ice on an ice particle just by the method that it's talking there. And I don't want to get in, and I don't think, looking at the ahead to the review questions, I don't think we all need to understand exactly how this works, but essentially the collision coalescence process works when you've got water droplet clouds, and that tends to be at the tropical or mid-latitude levels during the summer, where the Bergeron process talks about how ice accumulates. It starts with a small ice particle and then builds up ice over time, again, getting to the point where it has sufficient mass to be able to fall from the sky. Doesn't matter which theory you're talking about. Essentially what they're trying to explain is, well, how do you get something that is suspended in the air in a cloud? How does it come together to have sufficient mass, either as a water droplet or as an ice particle, so that it falls? And these two theories kind of explain that. I always found this picture really interesting because I didn't know this, but essentially here in the mid-latitudes, everything in the clouds, or nearly everything in the clouds, starts as snow. So even on a summer day, it's probably going to be snow up in the clouds initially. But then what ends up at the ground is a function of what that snow falls through. So if you start over on the far right, the clouds create snow, the ice particles come together, they create snow of sufficient size and weight to fall from the clouds. It falls from the cold, relatively cold clouds into the still cold air. So it starts as snow and it ends as snow. The next one to your left starts as snow. It melts in the warm air, and then that rain falls into the cold air, where it freezes on its way down. So it hasn't made the surface yet. So what gets to the surface is sleet. Freezing rain starts as snow, gets into the warm air and melts, stays as in liquid form until it gets to the cold air at the surface, where it turns into ice. Now, depending on how fast that ice freezes, how fast that water becomes ice when it hits the surface, it either becomes rime ice, which is rain that pretty quickly, nearly instantaneously, freezes when it hits a very cold surface. Or the raindrops are sufficiently large, or the surface is not so cold as to freeze it immediately on contact, in which case the ice builds up. And then we'll see in the next slide, that on a ship especially, for example, you can get a thick layer of ice that affects its stability because you've added all that weight above the water line. But there's two different kinds of ice that form, freezing ice and rain that form.
Glaze ice is the second one, glaze.
Thank you. So if on the last picture to the left, it starts as rain, as snow, it warms itself up and melts in the warm air on its way down, and it falls into warm air. So it started as snow, it melted on its way down, and it arrived as rain. Any questions on that? Okay.
Well, how do we form hail? I mean, it's the obvious question that's not on there.
That's coming. Thank you.
Okay.
I'm going to say it's a slide or two ahead, but good question. Great question. So they measure drizzle. There's two kinds of let's talk about drizzle. Let's talk about rain. We'll talk about snow. But they use different ways to measure how much we're getting of that particular form of precipitation. Drizzle is measured by visibility. How far can you see? So the heavier the drizzle, the less visibility you have. When it's actual rain that is falling, it's then measured in inches per hour. Now, I guess the obvious question is, okay, at what point does drizzle become rain? And my answer would be, well, when I can measure it in inches per hour, it's rain. It would take a lot of hours to get measurable in a rain gauge drizzle collected. So drizzle is that kind of stuff that soaks you and freezes you to death in Chicago or Boston. Rain gets you there quicker. In snow, they tend to measure, again, in terms of what the rate of precipitation is, visibility. Obviously, somebody goes out there with a ruler and measures the snow on the ground in accordance with, appropriate standards, and there's a methodology as to how often you can, what the size square is you're supposed to be measuring it in, and how often you clear it off, and all that other kind of stuff. But snow, that the rate of snow falling is a function of visibility. So other types of precipitation, graupel is that kind of, it sort of reminds me of the things that you can buy ice cream pellets at the store, where it's not hard. It sort of looks like miniature hail, but it's not hard. It's kind of fluffy, and you can crush it between your fingers. Snow grains are effectively the frozen version of drizzle. Ice crystals are really tiny, and I'd have a hard time distinguishing between a snow grain and an ice crystal, and even if they were hitting me in the face. Sleet makes a little more impact, so I know what sleet is. And now we're talking about, we mentioned freezing rain, and it's really a function, well, how big are the raindrops? If they're drizzle, then when they hit a cold surface when they hit a cold object at the surface, they form rime ice. But if it's truly rain and not drizzle, and it takes longer for that rain to freeze, so that it wets the surface, it freezes, then it gets wet again, it refreezes, you can get a lot of ice buildup. And it's especially dangerous, as the slide notes, for boats, in that it makes them top heavy and can very adversely affect their stability, which is why sometimes you see pictures in old movies of guys out there with axes and sledgehammers trying to break the ice off of their boat. Sometimes that's from the spray plowing into the ocean. Sometimes it's from the combination of the spray plowing into the ocean and the precipitation that's freezing on the halyards and everything else. Hail is formed when you essentially take an ice particle and you put it in a dew loop in a thunderstorm. So it gets heavy enough to fall, it starts to fall, and then it gets caught in an updraft. So then as it's rising in the updraft, it gets weight, more ice added to it, another layer. It gets heavy enough to fall, so it falls towards the surface. And if the storm is particularly robust and has these kind of internal cells going on, it can do that cycle multiple times, where it starts to fall, gets caught in an updraft, it gets a layer of ice put on it, it starts to fall, it gets caught in another updraft, it gets another layer of ice put on, and so on. I saw something, there was 3.5-inch hail in Chicago, if I remember right. Parts of Chicago, but Bill Luckshaw, I saw you on the call. Didn't you have something roughly that size at your house a week and a half ago or two?
Yeah, that's right, Dan. There was about at least golf ball size.
So, but hail is only comes in thunderstorms where you've got that kind of inner cloud dynamics, where there are essentially cells, vertical cells within the cloud that is circulating, picking up the the frozen precipitation and taking it back to the top of the cloud where, and then doing that over and over again. So you don't see hail come out of any cloud other than a thunderhead or a cumulonimbus. Does that answer your question about hail?
Yeah, thanks. Actually, I saw it in the book too. I'm reading along. I didn't have time to study before the class this time, or I wouldn't have asked. Thanks.
Okay. What is the weather situation here? Anybody want to tell me what this is saying? Our station model?
Okay, I'll take a crack at it a little bit. You've got the wind coming from the southwest at 15 miles an hour. The temperature is 67 degrees Fahrenheit. You have these two cloud symbols right up at the top, which I'd have to refer to. You have barometric pressure of 965 millibars, and it's dropping at 23 millibars over 3 hours. And then just from reading the text, you're talking about 3/4 cloud cover. And the other things I think I'd just be guessing at.
Well,
warm front.
Yeah, the 67 is the air temperature, right? 49 is the dew point. There's a mile of visibility, and the two little dots says that there's light rain. So what's about to happen, or what's going on? So the winds from the southwest, falling barometer, and light rain. You've got clouds at all three levels, is what those symbols are telling you.
A warm front.
Yep, it's a warm front that's approaching.
Also remember, if you could go back, if the speed's going to be in knots, right? So it's not 15 miles per hour, it's 50 knots. And the decrease in the pressure is 2.3 millibars, not 23 millibars, 2.3.
Okay, well,
Okay. Section 3. Any other questions on section 2? All right, so we're going to talk about coronas, which are weather phenomenon, but not the beers, halos, and rainbows. So this is going to be kind of like magic in this part. You see people sometimes on television talk about, I'm a meteorologist, and somebody says, oh, so you study shooting stars? Yeah, I guess, because anything that's in the atmosphere is called a meteor. So that can in fact be shooting stars, but it can also be things like clouds, precipitation, dust, whatever. What we're going to talk about in this section are photometeors, which is halos, coronas, sun pillars, sundogs, and rainbows. So when light from the sun or the moon enters the atmosphere, one of four things, or more than one, but four things can happen to it. It can be absorbed. So the energy, and that's what you guys all learned in chapter 1, that when the sun's energy hits the earth, an awful lot of it goes into thermal energy or heat. So the atmosphere warms. It can be reflected, which means it kind of gets bounced off, and just think of mirrors. So it moves in a different direction without any change in its character. It can be scattered, which means it's kind of, and I loved what the book talked about, waves hitting a rock. If you think about water coming downstream and it hits a rock, on the back side of it, there's a little bit of chaos. So you'll see a V where the water is spread out by virtue of hitting the rock, and then you'll see stuff in between the V of the downstream wake that are eddies and currents and what have you. The same thing can happen when light hits air molecules and water droplets and ice crystals in the sky, it gets kind of scattered everywhere. Or it can be refracted, and the easiest way to do that, in the slide coming up will make it clearer, is just think prism. You know, light going into a dense material, denser than air, gets bent differentially. It gets spread out a little bit. The colors get separated depending on their wavelengths, and so and the colors are a function of their wavelength. So if you think prism, that's what's going on. Air molecules scatter blue light more than red. You know, rather than get into, I mean, I think that over on the right side of the slide, if we're talking about the river analogy, this is the size of the rock that the river is running into. So light is coming in, it runs into really small particles. It gets kind of scattered in pretty much all directions. But if it gets into little bigger molecules or into air droplets or what have you, or water droplets, it tends to propagate, go around it, and more of it goes past it as opposed to reflect off of it. It gets stopped and then flows past it as opposed to being bouncing. Think of it as, this isn't accurate at all, I think, from a physical or scientific point of view, but if you're going to use the river analogy, you know, the current of the river keeps the reflection down when it bounces off a small particle. And a large particle does even more of a focus down stream from the particle. So air molecules, water droplets or ice particles are the middle, the small, and then water drops or raindrops or actual ice crystals are the large thing. But off of this slide, what you really want to do is you want to remember that air molecules scatter blue light more than they do red. Jock, you have a question?
Not a question, just a comment that, you know, I can, you know, memorize this, but this does not make any sense to me, that something small would actually create more scattering than something large. That does seem completely counterintuitive. And so I'm just mentioning that as something that I have trouble kind of grasping. I'll just memorize it. That's okay. But don't ask me why. Okay, thank you.
Well, I think that, you know, we'll go over to the far left of the slide where it talks about, assuming that you have the same angle of attack on whatever it's running into, you know, the ratio of the wavelength of the light coming in to the size of the particle that it's hitting is, you know, what creates the dispersion, the difference in dispersion patterns. You know, and like I said, in terms of what I remember from taking this class a long time ago, and even with refreshing myself for, you know, in preparation for tonight's class, this was something that I don't know that you really need to remember. The important thing is the part that's highlighted in red. Blue light gets scattered more than red light because it has a different wavelength. So if it, you know, hitting the same amount of you know, diverse size particles, blue light's going to get scattered more than red light. And why do we care? Because, you know, why is the sky blue? We'll talk about that in a second. Refraction is essentially, as it said there, depending on the density of the material that the white light is coming from and going into, it differentially bends the light, where in scattering, it differentially scatters the light, but you're in the same level of density. Air is fairly consistent for purposes of this conversation. And so you need to have a significant difference in the density of the object that the light is going from and into to have it refract. So the prism's the obvious one. You're going from air into some sort of crystal or glass that is causing the light to bend both when it goes in and then when it comes out. So you have light passing through the prism and creating a rainbow on the far side. Everybody got that? Can you picture this? Because we're going to talk about, rainbows and lollipops and other magical things in a minute.
Steve, if you want to share your thoughts, yeah, go ahead, speak up.
Well, what I had said is the way I look at it is if you have a small area, like say in your house, and you have the smaller the molecules are, the more of them there will be in that room. Therefore, the more the smaller the molecules are in the air, the more of them that will be there. Therefore, it will scatter that light more. So if you have less molecules, there's less molecules out there. The larger they are, the larger they are, the less there is. Therefore, they're not going to scatter as much light.
Well, that's a good point. The other thing that happens, given and I think you did a great job of describing it, Steve, is that you get scattering of scatters. So, if I hit a particle and it gets scattered, well, okay. But then if those beams that are scattered run into other particles, they get scattered again. And because the direction coming down, there's, after a while, 50% go by it and 50% get scattered, and then they hit a second one and 50%. So, I mean, the sky gets blue because it's all of the scattering across the sky. And it's not just the light that comes in and as a beam and makes it to the surface. It gets bounced throughout the atmosphere, which is what we see. But let's talk to that. So remember we said that blue light is scattered more than red. So it's this cross scattering that essentially fills the sky with blue. And if there were, I can imagine, a different planet and a different atmosphere, with a different sun, the sky might be a different color. It clearly is a different color if you put different particles in the air other than air molecules. So if you put soot or dust or smog, I was in Beijing a handful of years ago, and I kept thinking it was going to rain because the sky was always sort of this kind of overcast, hazy, bluish, brown, gray kind of color. And then when I left the city and got away from it, it was a very nice blue sky, but it was because the air was so filled with stuff other than air molecules that you were seeing those colors, and it was overwhelming the blue that was from the blue light being scattered in a clear sky. It was in fact highlighting the smog, the haze, the smoke, all that stuff that can fill our skies other than nice clean air. So if your kid says, why is the sky blue? Everybody has an answer, right? Somebody want to feed back to me? Why is the sky blue? I'd like to hear somebody kind of tell me that. Anybody?
Jennifer, you want to take a crack at that? Jennifer?
Sure, it's because of the way that the light scatters over the entirety of the sky, darling. And blue light scatters more than red light. And
Yep.
that's the light that we see.
I actually think that, thank you, Jennifer. I think the little graphic that they have there, thanks, Mom,
Sure.
is
Kids are in the next room.
because it shows the components of a white light from the sun coming into the atmosphere. So you've got blue lights and all the different wavelengths. At one end you've got red, and at the other end you've got ultraviolet and blue. And it's because the wavelengths are so much shorter at that end, they're scattered more by the molecules in the air, where the others get scattered a little bit. You know, green certainly does, and yellow does a little. I'm not sure I agree with 2 reds, a yellow, and a green all making it to the surface the same, because they get scattered a little bit, just not as much as the blue. So the blue sort of saturates the sky that we see on a clear day, obviously when it's daylight. Okay, so this is the one that I always had a hard time with. Kids, why does the sky turn red at sunset? You go like, well, the answer is, I guess, because the only thing that has has a wavelength sufficiently small to make it all the way through to our eye at sunset. Because the more atmosphere you go through, the more that light is scattered. So on that previous slide, remember I said I have a hard time because that suggests that, well, all your red and your yellow and your green make it, and it's only your blue that gets scattered. That's not true. They all get scattered, but the blue gets scattered more. So if you say, gee, there's a finite amount of these little packets of energy or photons coming in, if all the blue gets scattered on a clear day in the upper atmosphere, then and you see blue, that doesn't mean that the yellow component, those light waves that are of the wavelength for yellow or green, they get scattered too, just not as much as the blues. But by the time you go to sunrise or sunset, you've got a lot more atmosphere to go through. So the only wavelength that survives the transit through the longer trip through the atmosphere are the reds. Sometimes the yellows, occasionally you see a little green, but it's a function of if our atmosphere was thick enough so that all of the blues got scattered out and all of the yellows and the greens got scattered out, then our sky would look red all the time. That makes sense? But our atmosphere would have to be a whole lot thicker than it is for that to happen. And because it's not, that's when, during the day, the greens and the yellows can still get through, and the blues are the only thing that gets scattered into the upper ranges of the atmosphere and what we see. Make sense?
Could I ask a question and make things even more confusing than they are
Sure.
already? When you go submarine into the water, the red apparently gets filtered out quickly, and it's the blue that goes through the water. And by the time you get down a little bit underwater, it's all blue down there. And so again, don't ask me to explain it. I'm just pointing out this would seem to be the exact opposite of what we're looking at with the atmosphere.
Yeah, but the density of water is a whole lot greater than the density of air. And the amount of scattering is a function of the density of the medium that it's going through. So think about a prism, and again, I'm going to guess that the infrared or the reds get absorbed into the molecules, into water molecules, a whole lot easier and faster than the shorter wavelength blues, which is why, because it's more dense, it absorbs, something more dense absorbs it more easily. So it's a question of absorption versus scattering at that point.
Good. Joseph Laudano had a question.
Yes, Joseph.
Yes. And I'm going to apologize for the question up front because you may have answered this before, but could you explain the old adage, red sky in the morning, sailor take warning?
Red sky at night, sailor's delight.
Sorry for the question, but it's one of these, I always want to know why.
I can hop in if you need me to, Dan.
Well, go ahead, Bob, and I'll correct you if it's different than what I think.
So, in the event of a lot of dust being kicked up by the atmosphere, in advance of an approaching weather system, usually a cold front,
Mhm.
all that dust will scatter in the atmosphere, and the only light that can get through because of all the dust in the atmosphere is the red light. And so the sky will seem unusually red. Whereas here in this case, the sunset photo, you can see to the west, there's not a lot of dust in the air. So as it gets closer to the horizon, the red light at dusk or in the evening, you can see the sky to be red as opposed to cloudy or dark. And that indicates that there is not as much dust in the atmosphere. I don't know if that's clear enough. Does that make sense?
It does, yes. Thanks, Bob.
Yeah, I mean, the more dust there is in the atmosphere, the comment on the slide that's up there about volcanic eruptions, it's also true, you think about some of the sunsets and sunrises we had last year, I think it was last year or the summer before, when there were these humongous wildfires out west, dumping all kinds of smoke particles into the upper atmosphere. You know, the sunsets were spectacular. So because there was so much in the air, but it didn't necessarily mean a storm was coming or not coming. It just happened to be because the volcanoes had put so much stuff into the aerosols into the air.
And if I
Monique?
can stick my oar in, Bob.
Oh, please do. And then we'll get to Monique's question.
Okay, yeah, I like Monique's question too. But now the way I heard it with the red sky at night is that a red sky in the morning is reflecting off of approaching storm clouds. So it's the normal red light coming from the east hitting storm clouds to the east and causing them to turn red. Whereas at night, the red sky is passing through clouds that are to the west of you, which means that that adage only applies in the tropical easterly, the trade winds areas where the sailors saw this. In the mid-range areas up where we are, the exact opposite applies. But
Yeah,
so many
we may wanna
people have
double-
made so many comments about so many different ways trying to justify or argue against that. I'm not going to, so I'm going to be quiet now.
Yeah, I was going to say that in both Bob Allen's response and yours, Chaz, that assumes that the weather moves from east to west, which is true, as you observed, if you're in the tropics, and not so true if you're in Chicago. So, yeah, but most people didn't sail from Europe to the Bahamas via Chicago, so they were in the tropics. And I guess it made sense for them to come up with the adage.
And Monique, I think we'll get to your question after later on here, because I've got a nice video to share.
Okay. Any other
Thank you.
questions? So halos are caused by refraction, and refraction, remember, is a prism effect. So when the light goes through ice crystals, it's like, remember I said, gee, to have refraction, a light beam has to go through something that's pass through, not bounce off, has to pass through something that has a higher density. You know, and in this case, it's passing through ice crystals, which in fact break it into its component colors because the different wavelengths are moving at different speeds, essentially. You know, and what you see a halo or a rainbow sometimes around the sun. Halos in the west can indicate an approaching front because it requires high-level clouds. And remember, high-level ice clouds are oftentimes there because they are the tops of storm clouds or thunderstorms further away that are blown off. The tops of them are blown off and create kind of a layer of thin ice crystals in the higher atmosphere, over 20,000 feet level, that you then see a halo being formed when the sun passes through that. That makes sense to everybody? So halos are a function of refraction, kind of like a prism effect. Coronas are caused by a scattering. So, and they're going through water drops as opposed to ice crystals. Now, again, if you're going through a level of clouds that, in this case, you have water drops, where in the halo case, it was ice crystals, because there are clouds at the middle or higher level, you're seeing that's, an indication here in the mid latitudes can be an indication at sunset of an approaching storm. Makes sense to everybody? So coronas are caused by scattering, and halos are caused by refraction. Important, just in case you wonder. In the one case you see, in both cases you see the sun, or in one case the moon, is passing through those clouds, and it's not going through a denser material and being broken into its components. Although you see a little bit of that in the upper picture, it's mostly just being scattered around it. Sun pillars are reflected from ice crystals, where sun dogs are caused by refracted. So they are essentially, in the one case, it's being bounced off of and you see it. And that's just like every other cloud where the sun has set and now you continue to see the clouds illuminated. In this case, a pillar directly above the sun in the upper picture. And the other, if you didn't have the sun dogs are the things on either side of the sun in the bottom picture. You've got a significant corona-like or a halo effect around the sun in the middle, and then you've got the sun dogs on either side of it, the mock suns that are coming out. And that's because the sun is being sent to you in that look at the horizon. There was a lot of this going on in Chicago in the last month or so with a lot of how infrequently we saw the sun here. It seemed like our sunsets and sunrises had these features going on more than I can remember. So rainbows, just to confuse things even more, are both a reflection, a product of refraction and reflection. And so, and I think the graphic does a terrific job of showing that. So the white light or the sunlight that comes into a raindrop gets refracted, has that prism effect. It's broken into its various components, so the different colors given the different wavelengths of the light inside the raindrop. That's important to visualize. So sunlight enters the raindrop because you're going from one density into another. You have refraction occurring. The light beam is broken into its different colored components. it gets to the back side of the raindrop, bounces off the inside of the raindrop. So it's reflected. Then as it exits the raindrop, it's going from one density to a different density, so it gets refracted again. So the colors are further separated in space by having entered, being refracted once, and then exiting, being refracted a second time. And the end result is that you get a rainbow. Now you have to have the sun at your back in order to see, in this case, 2 rainbows. And I don't know that I've ever had the sense of mind to turn around and look into the sun to see if there was a 3rd rainbow. I didn't realize, one, that there were things as called tertiary rainbows. And I certainly didn't know that you had to turn around and look at in the sun's direction in order to see them. So rainbows are caused by the sun going into the raindrops themselves. You have to have rain out in front of you when your back is to the sun. You need to have clear skies for the sun to shine on that water, on those drops. And I think everybody has probably seen with the garden hose on their own rainbows when washing the car or watering their plants, and recognizes that, gee, I need to have the sun behind me and shining on those water droplets in order to get a rainbow effect. Okay, summary of stuff. Clouds are very small water ice particles. I mean, really small. And remember, by themselves, they're too small to fall out of the sky. So something has to happen to them. They have to, in some way. Yes.
Can we go back real quickly? Sean is asking about, just for a refresher on tertiary rainbows. He's asking whether you have to be looking towards the sun or away from it. So I'll let you explain that.
Toward it. Yeah, because essentially my memory is that a tertiary rainbow is caused by a double reflection inside the drop. So you would be facing the sun in order to see. There need to be, and I don't know how I'm trying to picture how to explain that, because I'm kind of going off of what the book said to me, but I've never seen one. And the book says that you need to look towards the sun, in the sun's direction, in order to see a tertiary rainbow if there is one. And my understanding is that tertiary rainbows come because you've got a double reflection or multiple reflections inside the raindrop before it exits.
Yeah, that's the explanation, Sean. That's how it is. He actually would be facing towards the sun. He's in disbelief, but that's also why they're extremely hard to see, because of that second reflection. And so they're very uncommon and very few people have seen them.
They're really, I mean, every time you bounce a little, you take another bounce inside a raindrop. I think, there's a picture there on this slide of a droplet. Remember, these things are pretty tiny, but there's no reason. I was looking at my aquarium the other day and trying to figure out why does the fish can see me, because when I look in, I just see a mirror. So I assume that the fish see a mirror too. Inside a raindrop, the inside of the surface of a raindrop acts like a mirror. It bounces off because it's a change of density. So there's an edge there, if you would, if you're a light wave. You've got to have sufficient, the right angle of attack, if you would, to bounce off of or to penetrate through that and get to the outside again, because you're going to get, you're going to have your path altered again when you exit and go into a different density. So there's tends to be a little bit, I mean, and we're only talking a small part of a light beam that's doing this. But the more directly the sun is shining on it, the more brilliant the rainbow. And every time you get another bounce inside the raindrop to create a second rainbow. You can see in the bottom picture how much fainter that second rainbow is. And that's because, you know, most of it hits the opposing drop wall, if you will, and then comes back towards us. If it bounces in there a second time before coming out, you've lost it, and it's being and it's going not necessarily directly towards you in terms of the different colors in any case, because it's even more scattered by having been inside the raindrop a little bit. I don't know, did that help or confuse?
No, that's fine. Yeah, that's about as good as it's about as clear as it's going to get. That's pretty much it.
Okay, so back to the summary. Remember, if it's a cumulus cloud, think about, I think a cauliflower. That's how I remember cumulus clouds. You know, but it comes from a Latin word that means kind of to make piles. Whereas stratiform are flat clouds or blankets. And cirriform is curly hair, so it's wispy strands kind of things. Wispy is probably the best way to describe a cirriform. So you got the three basic types: either they're puffy, they're flat and like a blanket, or they are wispy. And then you've got three different layers in which clouds can form. So what is the layer of cloud that only has one kind of cloud in it in terms of form? Anybody remember from that chart?
Cirrus.
Yeah. So high level, so above 20,000 feet, the only kind of clouds that are up there are going to start with cirro, CIRRO, because that they are ice crystals and they only form at 20,000 feet or higher. Where pretty much every other kind of cloud, whether it's cumulus or stratiform, they can form at every level, low, medium, or high. And again, if you see nimbo or nimbus, that either before or after a cloud's name, that means it's that kind of cloud, that particular type, and it's creating precipitation. Okay, I'm not going to spend a whole lot of time on this, but you know, precipitation starts as water or ice. Around here, it tends to always start as snow. Down in the tropics, where the atmosphere is somewhat warmer, it can start and stay as in liquid form, but around here, it's always going to be in ice or crystal form, or nearly always. And then depending on what kind of air it falls through, that'll determine what ends up at ground level where we are. Remember, picture, if you will, that one graphic that had a warm front that's the precipitation was starting in the clouds and falling through the warm front, and depending on whether you were in the warm sector or you were still in the cold sector, it defined what kind of precipitation you were going to experience at the ground level. Yeah. Light interacts with the atmosphere by being absorbed and being converted into heat, or being reflected, scattered, or refracted. And depending on what is happening to that particular ray of sunlight, you get these other effects that we were talking about. So the sky is blue because blue light is scattered more strongly and repeated and rescattered among the molecules in the upper atmosphere. So we see blue, where the blue and the green and the red continue on into where we are standing. But when we look up, we see blue. Yeah, but sunsets are red because of the extended length, depth, if you would, of the atmosphere through which the sun's rays are going at that point, the low angle of attack. They got to go through a lot more of the atmosphere So not only are the blues scattered, but the greens and the yellows are scattered as well, so that all that's left over for us to see is the red that we're looking into, and that's what gets picked up by our eyes and the clouds and what have you. Coronas are caused by scattering in water clouds, where halos are caused by refraction in ice clouds. So you can tell the difference between a cirrostratus and an altostratus, because a cirro, which is a high cloud, is in the high layer. It's an ice cloud, where an altostratus is a mid-level or a water cloud. And so you'll get coronas when you have altostratus, and you'll get halos when you have cirrostratus cloud. And rainbows are kind of, it's at the raindrop level, where it's acting like a little prism. Each raindrop is acting as a prism in its own right. And it's the sun entering the drop, being reflected off the back, refracted on the way in, reflected off the back, and refracted on the way out. And secondary rainbows have two reflections. And I never noticed, but I guess it makes sense that the colors are reversed. So you might, next time you see a double rainbow, you might want to observe that little piece of information. Okay, are we ready for questions? Anybody got the review questions at the end of the chapter? Anybody?
Bring it on.
Okay, Bob, I don't see everybody's name on my screen. Can you kind of?
Sure, I can hop in and hack away at this part if you like, Dan.
Okay, do you want me to, well, call on somebody and I'll just advance it when we.
All right, Joe Laudano.
Yep, Roger.
First.
Nimbus added to a cloud name means that it's precipitating.
Excellent rating, yeah, good.
There you
Jack
are.
Whittlesley, how about the next one? Clouds with a horizontal layered appearance are?
Stratus.
Stratus. Good. Chris
Stratiform.
McNamara, clouds with a wispy appearance are? Chris, you there?
Sorry, I forgot to unmute. Cirro or Cirrus?
Good.
Yes,
Oliver,
Seriform.
clouds with a lumpy appearance are? Cumuliform, good. Dave
Cumuliform.
McCullum, middle clouds are those that have bases between what altitudes?
With white with vanilla ice cream. Okay. She might like it.
About 6,500 to 20,000 feet.
Right on, excellent.
That's the middle.
Jennifer, we've already picked on you, so I'm skipping you. Bill Luckshaw.
No, I can do one.
Oh, okay. All right, next page, go ahead. What type of cloud would you associate with the phrase mare's tails?
Cirrus.
Right on. Bill Luckshaw, what type of cloud would you associate with the phrase mackerel sky?
Cirrocumulus.
Right on. Tony P, cirrus clouds consist of?
I believe it's ice.
Ice, excellent. Jeff Link, a wintertime deposit that can affect the stability of vessels is? You there, Jeff?
Yes, that would be the glaze ice.
Excellent. Ed Hallen, clouds that form caps over mountains are called?
Lenticular.
Excellent. Next page. Richard Clements, the reason the clear sky is blue is due to what fact?
The refraction of just the blue light. Not
Excellent.
everything else is dispersed.
No, you hit it on the head. Well done. Mike Patina, the clouds in the west at sunset are red due to what fact?
Due to the absorption.
Yeah, the other light, yes. So what you're saying is correct. The red light continues through. So the other wavelengths are scattered. So I think that's what you're saying there with
Yes.
absorption. That's right. Sean Buckmaster, halos are caused by what? You there? Oh, Sean has an issue with the microphone. Mark Bagley, halos are caused by what?
Ice crystals.
Excellent. How about James Zimmerman? Rainbows require.
Leprechauns.
Oh, he's having any lucky charms.
And/or
Rainbows require a sunlight past rainfall, and you have to be facing the rainbow.
Yeah, so clear sky behind in the direction of the sun, right? So I think you got pretty much all of it there. Joe Jackson, a ring around the sun or moon means that the clouds are most likely.
I'll pass on that one.
Monique, you want to take a stab at that one?
It's
Ring around the sun.
cirrostratus.
Stratus clouds, yeah.
Cirrostratus.
Right on. Richard Voss, I think that's it. That's it. So what we're going to do now is we're going to plug on through the questions at the end of the chapter, and I'm going to keep going from where I was going. Richard Voss, how about number one? Nimbo added to a cloud name means?
Precipitation.
Precipitation, excellent. Don Osiniak, clouds with a horizontal layered appearance would be?
A stratiform.
Excellent. Addison, clouds with a wispy appearance are?
It's cirriform.
Cirriform, yeah.
Cirriform.
Yeah, no, it's not a long E, that middle vowel there. JT, you want to take number 4 here? Clouds with a lumpy appearance are? You there, Joy? Can you unmute or you want to pass? Or you have the microphone issue too, didn't you? You there, JT? Michael, number 4, clouds with a lumpy appearance are? You there, Michael, or can you unmute? Somebody in here has trouble unmuting. Dave Watkins, you want to try that one? Clouds with a lumpy appearance are?
Cauliflower form.
Cumuliform.
I like Dan's description, cauliflower form.
Right on. Dave Watkins, can you unmute yourself or not yet? Dean Christie, number 5. Which type of cloud produces precipitation?
That would be nimbostratus.
Yeah, nimbo. It's a hint that there's weather. Good. Noah, how about number 6? Middle clouds range in altitude. Can you unmute yourself, Noah? Noah, who's on here?
I'm here. Number 6, middle clouds range in altitude between 6,500 feet and 20,000 feet.
Excellent. Back to you, Joseph. Number 7, low cloud bases are found.
That would be alpha below 6,500 feet.
Excellent. Don O, clouds that develop vertically are?
Cumulus.
Addison, number 9, what type of cloud would you associate with the phrase mare's tails?
That is also the cirrus.
Cirrus clouds. Dean Christie, did I already ask you if you can unmute or no?
Hold on. Yes, you did. I'm sorry. What number are we on?
Number 10, what type of cloud? Oh, no, we did already. No, number 10. I think we did do this. What type of cloud would you associate with the phrase mackerel sky?
C, cirrocumulus.
Good. Noah, back to you. Number 11, cirrus clouds consist of?
Cirrus clouds consist of ice particles. B.
Excellent. Jock, number 12, nimbostratus clouds produce?
Rain.
Yeah, whenever you see nimbo, just think rain. I'm a little confused here. Oliver, how about 13? Halos around the sun and moon are caused by?
Cirrostratus.
Cirrostratus. Good. Dave McCollum, 14. A heavy dark cloud from which a steady rain is falling is?
Nimbostratus.
Good. Now, why wouldn't it be cumulonimbus? It's surprising
Because
here with the sun. What's
It would be
that?
that would be a vertical, that's a vertical cloud.
It is a vertical cloud, but what they have talked to you about the books is if you have a cumulonimbus, you're going to have scattered rain. It'll rain real hard and then it'll stop. It'll rain real hard, then it'll stop. So for some of you that looked at that and got confused, that's what happened there. Jennifer 15, for precipitation to fall from a cloud.
The cloud particles must coalesce.
Excellent. 16, Bill Luckshaw, the factor that best determines the type of precipitation occurs precipitation occurs is?
The vertical temperature profile, A.
Good, excellent. That's a hard one for those of you that puzzled over that for a little bit. Remember, if it's, real cold, then it's going to be snow or something. But if it's going to be warmer, it's going to be rain. So that's how to figure that one out. Tony P, how about 17? Hailstones are always
Produced in thunderstorms.
right, because they go down, they go up. They don't go down, they go up. And every time they go back up again, they get another layer and get thicker. Jeff Link 18, the wintertime deposit that can severely affect the stability of a vessel is?
Once again, that's glaze ice.
Right on. Richard Clements, 19, rime ice is a deposit that forms when blank comes into contact with the surface.
B, super cooled water droplets.
Super cool, very good. Mike Patina, clouds that form caps on the top of mountains are called?
Lenticular clouds.
Yeah, that's a great graphic they had in this class. Very pretty. 21, Sean, the fact that the sky is blue results from? Sean Buckmaster? Oh, I did it to you again. Sorry, Sean. You know what? I'm just going to read the answer that you put on here and I'll share it with everybody. Blue light being scattered. Well done. Sorry about that, Sean. Mark Bagley, how about 22? Clouds to the west at sunset are red because?
I'm gonna say all of the above.
So they are looking for D on this one in their answer. Air to the west
that's D. I'm
scatters
sorry.
more. What's
Yeah.
that?
I said, yeah, D is all the above. I'm sorry. I should have
No,
said D.
D, in my book at least, it says D is B and C.
Oh,
It says the air to the west scatters more blue light. That's pretty close to being, something that is bang on too. What do you think about that? Did you see that one, Chaz? What do you think about that one? You got the questions? Dan, you got the questions in
Yeah,
front of you? What do you think of
was,
A? That's an interesting question.
Yeah, I mean, we talked about how it has a longer distance to go, so it's going to scatter more blue. I mean, it always scatters more blue.
Yeah, so maybe,
I think they're
maybe here's
being
another.
that's a true
differential
statement.
there.
I would have gone with D, just
D is the answer that's shown to be correct, but it says just B and C. I think they're being picky there, saying that the air to the west is redder than the air to the east, which of course it isn't.
Yeah, that's that's pretty good. All of the above sounds. I think if you see this question A, I'm going to tell you to go with D again and just say B and C, but I can see how you could argue that A is also correct. Pat Mussman, sorry I skipped over you the first time, Pat. Hey, number 23, halos are caused by?
All of the above.
Excellent. Thanks, Pat. Sorry, I skipped it. Chris, how about 24? Rainbows require, Chris McNamara?
Raindrops and direct sunlight.
Excellent. James Zimmerman, how about 25? Now, I got a lot of complaints from people saying, hey, wait a second, these last 4 questions aren't even from this chapter. And it's true. You're correct. But we're gonna soldier on here. James Zimmerman, to see a primary rainbow, you must.
The answer is A, you have to have your back to the sun.
Excellent. Joe Jackson, here's the first of those 4 questions. When a secondary rainbow is formed, it is fainter because?
I had D, none of the above.
I looked at that, but it does what Dan talked about is it's reflecting. It has 2 reflections inside the raindrop. So they're looking for A, and I think that's correct. It's interesting. They say C, colors are reversed, and that's a tricky answer because the colors are reversed, but that's not really the reason it's fainter. So I can see them throwing in there. That's a pretty fishy question right there. All right, and it's just the last 3. I misspoke. Monique, how about 27? An example of a synoptic scale phenomenon is?
An air mass.
An air mass. Yeah, I looked at this and the first time I thought it might be D, but I think an air mass would be correct.
All
So,
of
I mean,
these
you can have
are-
a huge air mass, such as the Arctic polar, but essentially you're going to have, just like the maps showed earlier in one of the earlier chapters, usually that's going to be not an entire global size phenomenon. It's going to be more of a
Bob,
synoptic
if
scale.
I could.
Go
page-
ahead. Yeah, go ahead.
Page 11 essentially has a definition of synoptic, mesoscale, and global scale. And it gives examples. And so the answers to 27, 28, and 29 are right off of page 11 in the student guide. So this is a review of chapter 1. If whether people wanted that or not, that's what they got.
All righty. 28, Richard Voss, an example of a mesoscale phenomenon is mesoscale.
Thunderstorm?
Thunderstorm. And Stephen Boyer, number 29, the trade winds are an example of.
We're gonna say the global scale phenomena, which would be A.
Good. Yeah, it's bigger than just a synoptic scale phenomenon. Now, in the chat, I don't know how many of you are reading all the chat stuff. Now, we had a comment from Jennifer. And you know, this gets into the whole red sky at night thing, which, yeah, we'll talk about for a second. So what happens is here in the mid latitudes, winds blow but prevailing westerlies. That means they come from west and blow towards the east. And as they're blowing towards the east, they're pushing dust out in front of it. So she makes a comment that dry, dusty air is moving away from you towards the east. That's pretty good. Yeah, she explains that pretty well. So it's to the east of you, but it's not moving towards you. Good. And let's see, somebody else, Mark Bagley, looking at the answer to question 22 in my book.
Oh, don't you dare.
Clouds to the west at sunset. Yeah, so this was it says that in your version of the book, it says that D is all of the above. Is that what you said, Mark? Can you talk?
Yeah, and that was the guess I made, but you said your D is just B and C.
Yeah.
And I'm missing the last few questions. So I think I have an older version of the manuscript here.
Well, now if you have the old book, you don't have the newest one. So I sent out a link to the newest book that I have, which I think is the newest one. Good. Other
Okay.
questions? Dan, you had other stuff?
No, that's it.
Chaz, do you have other stuff?
Oh, yeah, there was something I was gonna say and I can't remember now. And Monique had the question about the green flash. That's, you said you had a video of that, Bob?
Yeah, I have a video that appears to see it. So for those of you that haven't heard of it, the green flash is happening either at sunrise or sunset. This fleeting spectacle is caused by the refraction of sunlight, which is particularly significant at sunset and sunrise when light travels through more of the Earth's atmosphere. The atmosphere bends the sunlight passing through it, separating the light into its different colors, much like a prism bends and splits sunlight into rainbows. According to Cornell University, Dan did a nice job explaining this earlier. The various colors of light bend different amounts based on their wavelengths. Shorter wavelengths, blue, violet, and green, refract more strongly than longer wavelengths, yellow, orange, and red. As such, blue and violet light are scattered by the atmosphere, while red, orange, and yellow are absorbed, leaving the green light as the most visible during the few seconds when the sun sets below or rises above the horizon. Go to the next slide, would you, Dan? There, Dan. Can you go forward one slide?
That's what I got on mine.
All right, and we'll do a quick sneak. This is an introduction to the next chapter, which Chaz is going to get into thunderstorms, of which we've had a few around here lately. Is there another slide after that, Dan?
That's it.
All right, go ahead, stop sharing.
Yeah, just a comment that I have never heard of a green flash being witnessed on shore. And the green flashes that I've had people talk to me or describe to me have been as the sun out on the ocean drops below the horizon and its rays pass through the ocean. So you do have the ocean acting as a prism. And it's at that point that you get that, you know, when you think about a prism separating whatever light you've got into component parts, red and green, you know, are one of the things that will separate out. And as the sun sets into the water, if you will, you get it's very rare. Do you have a picture of a green flash or a video of a green flash?
I do. So the thing about it is,
I've seen it once.
What's that?
I think I've seen it once.
So the first 2 times I went through this video, I didn't catch it. And someone standing next to me said, "Did you see it?" And so the first time through, I was like, "No, I really didn't." So when you look at this video, it's only 11 seconds long. Look on the lower right-hand portion right here, and you can see just a little wink of green, lower right-hand corner. You see it real quick?
No.
We'll do it again. You really have to be watching for it. Look in the lower right-hand corner of the sun as it dips below the horizon. It's really faint. Did you see it at all?
No.
It's hard to catch it on film, I found, but you know, I stay in condos on the beach for months at a time, and I've seen it several times.
Uh-oh.
But it is quick, and once you see it a couple of times, it gets easier to spot.
And again, it's where the sun has sunk into the ocean that it occurs.
I'm gonna do it one last time, and then we're gonna call it good. Look on the right side, the lower right side. You see just a little glimmer of it? I had to watch it 3 times
okay.
before I actually saw it. I don't know if you saw that, but you can always go on my, oops. You can always go on my YouTube channel if you want to look at it. All right, team, any other questions?
Yeah, 2 things, Bob. One is I have seen a couple of pictures of the green flash. And it's my understanding that, yeah, you need a sea horizon because you need a sharp, clear horizon, but that the water itself doesn't do anything to it. But I'm not going to argue with Dan. And the other thing is that on March 19th, as I was coming back from that TCO class I did, I saw a beautiful sundog just as the sun was going down through clouds full of ice crystals. So yeah, there were a lot of sundogs and solar phenomenon in the past couple of months here out.
So Sean shared that in Gulfport, we see it over an island. Well, go ahead, Bill. You wanted to share something? Bill Luckshaw? You there, Bill? Oh, unmute yourself, Bill. Bill, you got to unmute yourself.
Okay, there we go. So I'm a sailor, it is my background, and I teach sailing, right? And so I want to teach my students wind forces when they're out there and how to drop or reduce sail as the wind increases. So I did some research on this, and I found that there's a scientific equation, a physics equation that describes this situation. And so it's basically the square of the wind speed is the force. So 10 times, 10 miles an hour is 100 force. 30-mile-an-hour wind is 900 force. It goes up from there. So it's logarithmic, increasing of the force as the wind increases. And all my, studying of weather. I never heard that really addressed. And I wonder if your course here addresses that.
I'm gonna wait till we get to chapter 8, and after that, we'll talk about that some more. Seems like I saw something in the textbook, but I want to double check.
Is it covered in violent storms, Bob?
Chaz, have you looked at that? Is that going to show up in the next chapter? Because I remember something about that.
Yeah, I don't believe it shows up in the next chapter 6. Maybe it does in chapter 8. My recollection going back to wind forces on structures is that indeed it is the square of the velocity with a correction factor based on the shape of the object that is being blown against.
Yeah, that's why I would, they have to figure that out when they're designing buildings or hurricane proofing them. So that's why I wondered if it was covered in the violent storm section.
I had to worry about it designing railroad bridges.
Cool. And Bill, if you don't hear that brought up in chapter 8, we'll bring it up again. Just flipping back through the chat, Oliver, I'm sorry I missed it. It says, what is a synoptic scale weather phenomenon? I want to say we covered that maybe chapter 2.
1.
Is it 1? Okay, so go back and reread that. So the thing to remember is global is like across the entire planet. Synoptic is like what you're going to see on the TV weather when they're talking about, oh, here comes some weather coming in from the west, and you got it's not the entire planet, but it's a fairly narrow. Mesoscale is going to be much smaller, like you'd see on a radar display when you're watching for a tornado or a thunderstorm. So that's going to be the next smaller one. So, but go back and check that out so you get a little more comfortable with that. Sean's got a math problem here. The final exam will not have calculus on it. I know you're all concerned about that. No calculus on the final exam. You guys go to turn
one
your
of the
camera.
things that the book talks about the difference between synoptic and meso and what have you is both the area and the time. So a global situation is measured over years, where a meso is measured over hours or minutes, and a synoptic's in between, it's days or weeks. So because it takes that long for an air mass to move across the country, for example, or to build in the first place. So a synoptic is one that's, several days to several weeks, I forget exactly, but the definitions for all that was given on page 11 in chapter 1 in the study guide.
Yeah, and I can understand being dissatisfied with the fact that, hey, wait a second, Mr. Allen, these questions are not from this chapter, and you're absolutely right. I think somehow they put them into this chapter because that first chapter had so many questions, they didn't want to blow people away, but you're absolutely right about it. This kind of winds down the critical part of the class. There was a gentleman, before I let everyone run away, and his name was Mike Smith. Mike Smith served in the Coast Guard, and then he moved to Michigan, and he organized a big fair to recognize the importance of the Coast Guard. And it's called Coast Guard Days in Grand Haven, Michigan. It's a week, a few days, 4 or 5 day fair they have right there in Grand Haven. And he's been running it the last 17 years, and it's a big carnival, big party, lots of food, lots of fun, and a lot of Coast Guard vessels come in, and to open public tours are given. So he passed away. So keep him in your thoughts and prayers. He passed on Thursday. If you guys want to turn your cameras on, you can. Because we're going to kind of wind things down now. What do we got? 47 after, maybe 10 minutes to go before the end of class. Any other questions? Does anyone else have any other questions?
Yeah, I got a question for you, Bob. When you look in the book, the very first sentence starts out says clouds are made up of minute water droplets, but there's no definition of that minute. Is that a mistake in the book?
If there's an E, yeah, I think what they're talking about is tiny or minute.
Yeah,
So maybe that's a poor choice of words maybe on their part, because they're talking about teeny tiny, like Dan was showing in that one picture, raindrops this big and a cloud water vapor molecule or a condensation is like this big. So minute is really what they were getting for, not minute. So sorry that threw you off. I would be confused by that too.
All right.
Monique, how we doing? Do we got you good and confused?
I'm fine. My question about the tertiary rainbow was really the primary and the secondary are visible to you when you have your back to the sun, correct?
Correct.
And then I remember the tertiary being facing the sun. Am I correct?
That is the definition. Now, I honestly don't remember ever seeing one, but I'm guessing there's some areas where the weather is just so where you can actually see one. But
Okay, but
obviously they're not going to make up something just to confuse us. We got any people here? Richard, you ever seen a tertiary rainbow? Because I haven't, but what they're telling us in the definition is you got to be facing towards the sun.
I guess my point is that, you have to face the sun to see it if it were there, correct?
I'm using their definition. I'm going to say yes.
Okay.
I've not seen
Thank
one,
you.
but I believe them. I don't think they're having a good time at our expense.
Hey, Bob.
Yeah, go ahead.
When you were talking about that, I kind of Googled that and it showed both ways. Like one of them, you're facing the sun, you'd see it. And sometimes they're showing where it's actually 3 rainbows you're seeing looking away from the sun.
Ooh. Well, I'm trusting these guys. And so I couldn't be burned at the stake for believing their definition, but that's what I believe. Don't burn me at the stake.
I would guess that the size of the raindrops that the sun is going into is a function of both the intensity and the number of rainbows that it's going to produce. So if you've got a downpour of those big honking raindrops like you see sometimes in a thunderstorm, and there's enough of them and big enough, maybe it's easier for the sun to bounce off of that and to throw a third one up on top of the primary, the secondary, and then a third one. Because when I think about when I've seen duplicates, it's always been a very heavy rain shaft that the sun is shining into that produces a double rainbow.
Go ahead and unmute yourself, Jennifer.
Shoot, I found a diagram of it.
Very fancy. You see, Monique, I'm not making it up. It's a real thing.
It's a real primary and secondary bows of a rainbow, sun at the horizon at 42 degrees. The violet is on the top part, the red, and top drop produces a secondary bow. The bottom drop produces a primary bow. And there's a little diagram in my little.
Nice.
Nice. I just saw a photograph of a quadruple rainbow observed.
Wow.
Nice.
It looks like 4 rainbows there.
Any other questions before we can stay around and visit? Does anybody else got any more questions about the class? Good. Now I'm going to start picking on people. Dave Watkins, are you there, Davito? Can you hear me? I don't know if Dave's really listening. Are you listening, Dave? You got to unmute yourself. No, he's not listening. Now, Michael, is that Mike McGann? Who's Michael? Can you unmute yourself? Picking on the people that weren't able to unmute themselves, so kind of mean, right? Joseph Laudano, is the bark in the harbor there?
It's yes, I know it's where is it now? It's not, this picture is of obviously in New London. It is, yes, it's at station. It's just up from station at City Pier.
Nice.
Where it is, yeah. And I just wanted to share a really nice photograph if I can, if you can.
Please do. You want me to set you up to share it on your computer?
Yeah, please.
Yeah.
And I'm going to show you a beautiful picture that we took on patrol a few years back with a multitude of different clouds here. Can you see it all?
Oh my.
Nice.
Wow. So this is off of Fisher's Island facing west from Fisher's Island, where we have SARDET, which is a search and rescue detachment. And I always wondered about this. This is not Long Island, and this is just sort of a color bar in here based on some kind of system, because looking west is only Little Gull Island and a few other things. But look at the different structures of clouds here. And I mean, it's just amazing. And that's why I saw the picture and I'm like, I got to ask that question about red sky at night.
That's a lot of different cloud levels there too.
Yeah. It's
Great eye
amazing.
behind the camera.
And then there's another one here, Race Rock. And that's another word just going down. This is probably, I would imagine if I was watching, I could have probably seen a green flash because this was just going down, you know, and all. But this is one of the most craziest, tortuous areas that we have in our AOR. A lot of boats crack up over here. So, yeah. I'll stop share. Thank you for letting me share that.
Thank you.
Good. All right, Dave, any other closing thoughts?
No, I'm good. Good luck to everybody.
You're welcome to come hang out with us as much or as little as you wish in the rest of the class. We don't have Samantha here tonight. She probably told me exactly where she's going to be. I feel guilty. I don't know. She might have a flotilla meeting tonight. So, I should stop recording this. Nobody leave the room.